Hello everyone, thanks so much for being here. I'm sorry that tonight is going to be cloudy, but I'm showing you a couple of planets. It's not the same thing as seeing them in the sky, but hopefully it's going to be good enough. So today we are going to talk about how to form planets, and what I would like to give you is like a recipe to form different kind of planets. But before starting, why are we interested in planets? Well, first of all, we live on one planet, so I mean, it's interesting enough to learn a lot about our own planet. So we live on Earth, and our planet is in a planetary system. So these planetary systems are orbiting around the star. Our star is called the Sun. And you see from this image what are the planets belonging to our planetary system. So the first one, the smallest one, is Mercury. It's very close to the Sun, and it's a rocky planet without any atmosphere. Then we have Venus. Venus is very similar to the Earth. It has a very thick atmosphere, and the size and the mass is very similar to the one of the Earth. Then, of course, we have the Earth. We live on the Earth, and the Earth has also a satellite, the Moon, which is orbiting around the Earth. And then we have Mars. Mars is another rocky planet. It's a bit smaller than the Earth, and also Mars has some satellites. And then, in the outer part of the solar system, we have different kind of planets. So we have Jupiter. Jupiter is the biggest planet in our solar system, and it's called the gas giant because it's not made of rock, as for example the Earth or Mars, but it's made of gas. Jupiter itself has several satellites, and some of them are really interesting because the effect of Jupiter can drive a very interesting phenomenon, for example, volcanism, or can create also some liquid water inside in these satellites. Then we have Saturn. Saturn, I think, is one of the most beautiful planets, for sure the most beautiful in our solar system. It has this wonderful system of rings, and it also has some moons outside of the rings. And Saturn itself is a gas planet, a gas giant. It's a bit smaller than Jupiter, but it's comparable. And then we have the last two, Uranus and Neptune. The two of them are gas planets as well, and they also have systems of satellites around them. And so I think that with this description you realize that there are two big families in our solar system. So we have the inner rocky planets, Mercury, the Earth, Venus and Mars, and we have the outer gas giant planets, so Jupiter, Saturn, Uranus and Neptune. And so these are the planets we know because they are the one we are in our solar system. But in 1995, the first exoplanet was discovered. So with exoplanet, I mean a planet that is orbiting around a star that is not the Sun. And in this case, in 1995, the first exoplanet ever observed is called 51 Pegasi b, and is around a star called 51 Pegasi. That's why it's called 51 Pegasi b. And since 1995, we have been observing a lot of exoplanets. So this is just an artistic representation of the exoplanets we have been observing so far. So, of course, since they are very far away and they are very small, we can't really see the surface of these planets, but this is like an artistic representation because with our observations, we are able to understand, for example, what is the mass of the planet, the size, and so we can have an idea of the composition of the planet. And you see that these planets are very different. So there are very small rocky planets, big gas giants, and the diversity of these planets is very big, and a lot of these planets are not present in our solar system. So there are planets that we have never heard before, and a very simple characterization of exoplanets is the one I'm showing you here. So what are the exoplanets types? So there are terrestrial exoplanets. We know them. The Earth, for example, is a terrestrial exoplanet. So these are planets with the size of about the Earth, made of rock, And according to their position, so how far they are from their star, they may have water in liquid state. And so these planets may be a good environment for life to form. And then we have super-Earth. So super-Earth are not present in our planetary system. These planets are terrestrial planets, meaning that they are rocky planets, and it's possible that they also have water, but they are bigger than the Earth. So they are more massive than the Earth, and so the gravity acceleration is stronger in these planets. And that's why they are called super-Earth. These are very, very common when we observe exoplanets, and they are not present in our planetary system. Then we have Neptune-like planets. We have, of course, Neptune in our system. So these are different planets because they are gaseous planets, so they are made up of gas. And Neptune is like the typical example of these kind of planets, but there are also some other different exoplanets called the mini-Neptunes. So these are smaller than Neptune, but still they still contain gas, and we don't have any mini-Neptune or sub-Neptunes in our planetary system. And also these ones are very common when we observe the exoplanet population. And finally, we have the gas giants. So in our system, we have two gas giants that are Saturn and Jupiter. And these are pretty common when you observe other exoplanets because they're also the easiest one to observe because they are bigger, and so it's easier to probe them. And, but there is a very different category of these gas giants that we don't have in our planetary system that are called hot Jupiters. They are called hot Jupiters because they are planets similar to Jupiter, but very, very close to the central star. So like at the distance of Mercury, for example, or even closer. And these are very common and are the easiest exoplanets we can observe. And actually, the very first exoplanet, 51 Pegasi b, is a hot Jupiter. So it's of the mass of the order of Jupiter, but is very, very close to the central star. And so I showed you that there are very different kind of planets, different characteristics. Liquid water can be there, rocks, gas, but how they form. So the main question is how can we form these very different sets of planets? And so to do so, we need to understand where planets form. And first of all, we need to understand the location, the exact location in the galaxy where this happens. And this is the molecular clouds. So molecular clouds, as the one I'm showing you here in this wonderful image, are clouds of gas. And they are called molecular because the gas that is composing these clouds is usually molecular hydrogen. And these clouds are present in the galaxy. They are also, we have molecular clouds close to our sun. And in particular, in the densest part of these molecular clouds, called molecular cloud core, that are, for example, the one I'm showing you here, the process of planet formation takes place. In particular, you see this is a very dense molecular cloud core that appears like just a black dot. This is because the density is so high that this cloud is completely blocking the light coming from things that are below it. So the density is so high that these molecular cloud cores basically collapse under their own gravity. And in particular, what happens is that they collapse because they are very dense and very massive, but at the same time, these cores are also rotating. And so whenever something is collapsing and rotating at the same time, what happens is that you can create a very, very dense object at the center, that in our case is the star, and around this object, you will form a disk. So basically, the material, while collapsing, will form a disk around your central star. And these disks are very, very important because they are the environments where planet formation takes place. And this is just a summary of the star and planet formation process I've showed you, I've talked to you about so far. So we can start from the top with a giant molecular cloud. we focus our attention in the densest part of the molecular cloud cores, that are rotating and collapsing at the same time, and they are forming these structures. So a central star with a gas disk around. And finally, the next stage, the next evolutionary stage is a planetary system. So a star with planets around. And we are particularly interested in these disks. These are called the protoplanetary disks because are the environments where the formation of planets take place. So what is a protoplanetary disk? So I showed you how we can form these protoplanetary disks. And so now we want to understand a little bit more what is the composition and how we can form planets inside them. So protoplanetary disks are mainly composed of two ingredients. The first one is dust. Dust is, we call dust, let's say, any solid particle in the disk. So these solid particles are usually silicates. But what is important is that the dust is very low in mass. So it doesn't really matter when we look at the total mass of these disks. But dust is very important because it can emit light. And this is what we observe. So this is, for example, an actual observation of a protoplanetary disk. And in particular, this is how the dust component looks like inside this disk. And the second component in protoplanetary disk is the gas. Gas, as I told you before, since it is inherited by the molecular cloud, is mostly composed by molecular hydrogen. And molecular hydrogen actually is very difficult to observe in these conditions. And so what we usually do is to rely on other complex molecules that are present in these disks. But what is important about the gas is that it dominates the mass. So it's of the order of 99% of the total mass of these disks. And so understanding the dynamics of gas, so how the gas moves inside this disk, is basically telling us all the information we need about planet formation. And so if we just think about these two components, they can remind us also the two different kinds of planets we saw before. So dust, it's like, as I told you, is composed of solid particles. And this can remind us, like, for example, rocky planets like the Earth. So the Earth may be like a result of growth of dust from small grains into planetary sizes. And for the gas, of course, this reminds us gas planets, for example, Jupiter. So these two components are actually really related to the different planets one can form in these disks. And just to show you how can we observe the process of planet formation, so how can we observe these protoplanetary disks? So we rely on this observational facility that is called ALMA. And you see, ALMA is not like a normal telescope. So it's not a telescope with a big lens and you look inside it to see what's in the sky, but it's like a collection of antennas. And so the idea is that these antennas can be moved in the desert. This is an image of ALMA in the Atacama Desert in Chile. So these antennas can be moved in the desert, and they will the signal from a system you are observing is arriving to the observatory, and basically by collecting the signal from the different antennas, we can then reconstruct the image of the sources we are looking into. And we need like this kind of observational facility, so like antennas rather than a single telescope, because the objects we are observing are very small and very far away. So we need to resolve them very well. And this is not possible with a single big lens, but we need different antennas to collect all the signal we receive. And so these are, for example, other observations of these protoplanetary disks with ALMA. This is how the dust is emitting in these protoplanetary disks. And you see that, I mean, they have very interesting shapes. So they have a lot of so-called substructures. So you see that these disks are not just flat disks without any features, but they have a lot of different things going on there. For example, you see disks with gaps, with rings, and you also see spirals or non-axis symmetric features. So you see a lot of different features in these disks, and we want to understand how these features are connected to the possible presence of planets in this system, because I remember you that these are the environments where planets form, so we expect planets to be there. And in particular, so if we zoom in into, for example, two of these systems, you see these are two disks with gaps and rings, and if we want to understand whether there are planets or not here, what we usually do is to say, okay, if there's a planet forming in this disk, what the planet would do would be to carve a gap. So basically to dig a gap inside this disk. And so usually what we do is to say, okay, we suppose that these gaps are generated by planets, so we expect to observe two planets in these protoplanetary disks. And so if we look back at these observations here, you see that almost all the disks have these gaps and rings, or this substructure in general. So we expect that planets are really present inside these protoplanetary disks. And so now we want to understand how do we form planets. So now I try to introduce you the environment of where planets form, and now we want to really understand how we can form planets. And I will focus my attention on two different kinds of planets: gas planets and rocky planets. So in this case, Jupiter and the Earth. And what I want to do today is to give you like a recipe for forming planets. And in particular, I think that forming a Jupiter-like planet is very similar to bake a mug cake, and you will understand why later. And to form a planet like the Earth is like preparing a Christmas pudding. And now I will try to convince you that this is the case. Probably preparing a mug cake or a Christmas pudding at home is easier compared to forming Jupiter and the Earth, but you can try if you want. I'll give you the recipe now. So now we want to form a gas planet, so we want to form Jupiter. So what are the ingredients to form Jupiter? So to form Jupiter, we need 10 to the 30 grams of molecular hydrogen, approximately, like grams plus or grams minus, so it's order of magnitude. And, but it's very simple. The ingredient list is this one. So we just need one ingredient. We just need hydrogen. While for a mug cake, we need just not many ingredients, actually. You just need flour, sugar, and eggs. Nothing more. If you want to put chocolate, then you also chocolate. But it's very simple, the ingredient list. And what's the preparation? So what are the instruments we need to create these planets? So to create Jupiter, we just need gravity. And in particular, the gravity acceleration is 24.79 in Jupiter. And so we just need gravity to create Jupiter. And to bake a mug cake, you just need a fork and a mug, nothing more, because the only things you need to prepare this cake. And finally, what are the times, the preparation times? So to form Jupiter, we will use this planet formation theory, which is called gravitational instability. I will explain you later what it is. And it's a very fast process because it takes just 100 years. I mean, fast for astronomical times, of course. And at the same time, for a mug cake, we just need a microwave. And like in 2 minutes, the mug is ready. So it's very, very fast and very few ingredients to create Jupiter or to bake a mug cake. And so, as I told you, the way to form Jupiter is through this mechanism that is called gravitational instability. So now I will show you a simulation. So this is a computer simulation of the formation of a planet like Jupiter. And so this is the disk. At the center, we have a star that may be the sun, for example. And the idea is that we have a disk that is very massive. So there is a lot of mass in the disk. And since the disk is so massive, it can be unstable. And when the disk is unstable, this is what happens. So you basically form this spiral pattern, and eventually you see that, I will show you again, you form these spirals which start rotating, but the spirals are so dense that you see you form a little clump there, and this is how you form a planet like Jupiter. So the idea is that you have a very massive disk. This disk has spirals because it's unstable, and part of these spirals can collapse, forming a planet like Jupiter. So this is the process that is called the gravitational instability, and as I told you, it can explain the formation of gas planets because it involves just gas, and it's very fast because it can form these planets of the order of hundreds of years. And so now let's try to, I will give you also the recipe to form Earth like the Earth, so a rocky planet. And I will convince you that it's very similar to prepare a Christmas pudding. And so what do we need for the Earth? What is the ingredient list? So that we need so many things. We need interstellar dust that is composed of silicates, ice, and also complex gas molecules. So we need really a lot of things. The list would be way longer, but here I just showed you like the most important ingredients, but we need a lot of ingredients for the Earth. And at the same time, for a good Christmas pudding, we need a lot of ingredients. So we need raisins, candied fruits, orange zest, flour, sugar, butter, eggs, milk. We need a lot of ingredients. So the ingredient list is very long to form, to create the Earth. And what are the preparation? What does the preparation involve? So it involves, like for the Earth, collision between dust grains, and then we need a lot of chemistry because these dust grains, once they collide, they need to chemically react to stick together. And at some points, we also need the gravity to make the Earth to stick together. So, I mean, the preparation is very complicated, and at the same time, also to prepare a good Christmas pudding, you need a lot of like hard preparation. So you need the fruit to mature, you need to bake some parts of the cake, and so on. And finally, so how long does it take? So to form the Earth, we will use this theory. It's called core accretion, and it takes million years. So you see that compared to the previous scenario, it's way longer. And at the same time, to prepare a good Christmas pudding, you need at least 6-10 weeks. So yeah, this is why the Earth is very similar to Christmas pudding. And just to tell you a little bit more about this core accretion theory for planets. So the idea of this theory is that in this disk, at the beginning, you have very small dust grains. So you have these solid bodies which are like of the size of micron. And it is that, as you see in this movie, this is a movie from a laboratory experiment. What can happen is that two dust grains collide and they can stick together. So the idea is that dust can grow in these environments, and this can bring you from very small dust grains, so micrometric dust grains, to centimeter dust grains, meters, kilometers, and eventually, for different physical processes, also bring you to the formation of a planetary core, so of a rocky planet. And but as I told you before, this theory is very, it's difficult to form a planet like the Earth because it takes a lot of time, and you also need a lot of ingredients. So the environment, so where this happens, is very important. But still, this is like a theory that works and can explain the formation of these rocky planets. And now, before concluding, before I told you that these planets, once they interact with the material in the disk, they can carve gaps, create substructures like the one I showed you in the observations. And so here in this slide, I'm going to show you a video from a computer simulation, another computer simulation, of a planet inside this disk, and you will see how this planet interact with the surrounding material. So in this simulation, you have a disk. At the center, you have the star, and the the white dot on the right is the planet. And so now the simulation will go on. And so what happens is that this planet is orbiting around the star, and is also like collecting a lot of gas that is present in the disk. So the mass of this planet is increasing more and more, and you see that is perturbing the disk, creating these spirals, which and then will just carve the gap as the one I showed you in the observations. So that's why we think that whenever we observe a gap, it is possible that there is a planet. And yeah, so what do we do like when we study these systems? So the idea is that we have observations of these protoplanetary disks, and to understand what's going on there, so what are the physical processes happening there, what we do is to perform these numerical simulations. So we have our big computers, and we input some parameters, and we see how the system evolves. And the idea is that we can then create some images that try to reproduce what we see in the observations. And here in this slide, I'm showing you both observation on the left and the output of one of our numerical simulations on the right. And you see that, I mean, the morphology and the shape of this disk is very well reproduced by our model. And in order to create this morphology, what we did here was to, for example, put 3 planets, and that could carve the gaps you observe in the simulation. And finally, this is the last image I want to show you. This is another observation. This system is called PDS-70. And what is very interesting about this system is that you see a bright ring, a bright dust ring, and inside you see this little spot, bright spot, and this is a planet. So this is one of the first directly imaged planet inside these protoplanetary disks, to show you that we can actually see them under like particular conditions. And yeah, so with this I leave you with my conclusions. So I hope you that tonight you learned that there are different planets can form in different ways. And forming gas planets is very fast, requires few ingredients. It's like preparing a mug cake. While forming terrestrial planets is a very long process. It requires a lot of ingredients, and like it's more similar to a Christmas pudding. And yeah, with this, thank you very much for your attention.
Wonderful stuff. Thank you so much, Cristiano. Do we have any questions? Yes.
Thanks, Cristiano.
Thank you.
You said in the protoplanetary disk, it's like 99% hydrogen and about 1% dust, which is mostly silicon. What's the original source of those silicons?
The original source of dust, you mean?
Yeah, they finally gave us hydrogen and some helium.
So yeah, the idea is that this dust is present in the so-called interstellar medium. So in the galaxy, the space between like different stars is filled of this fluid, which is called interstellar medium, and is composed mostly of gas, but it has also traces of dust. So it's basically interstellar dust that is basically inherited from the gas, from the molecular cloud up to the protoplanetary disk. So it's material that is already present in the galaxy that is filling the space between stars.
Mm-hmm. Fantastic. Anyone else? Yes, in the center.
Can you actually make a planet? Like, a planet?
Sorry?
Can you actually make a planet?
What do you mean?
Do you mean like, can we actually make a planet?
Okay, I mean, as I showed you, we can like make planets inside in our computers, so we can like create planets in our simulations. Actually, doing it like physically speaking, it's not really possible because we are on one of them. But in our like simulations, we see planets forming, and it's pretty cool.
It'll be in a few thousand years, right?
Yeah.
Yes, question in the back. You go nice and loud.
Okay, so they form basically when this cloud of gas, as the one I can show you here, where it is. So basically, when you have this, these clouds, these very dark clouds that are very dense, basically they are so dense that they are collapsing because their mass is too high, and so within this, when they are collapsing, you basically can form a star at the center, and then you form the disk on where the planets then can form.
Yes.
In the last simulation, when the planet forms the gas,
Yeah.
the direction of the orbit of the planet around the star changed. Why did
The distance, you mean?
it literally went in the other direction?
I think this is just okay. No, I think this is just a problem of how the video has been made. So it's just how many time step we are taking. But no, the direction is always the same. But it's true that at some point it seems that it changes direction. It's just like a problem of time frame in the video. Yeah.
Is it a bit like, have you ever seen one of those videos of a car?
Yeah.
It looks like the wheels on the car are going
Yeah.
back?
Yeah. Yeah. It's the same thing. Yeah. Yeah.
There was a question. Inundated with a question. Yes, please.
Is it the same process to create a galaxy?
Oof, that's a good question. Well, create a galaxy is a bit more complicated rather compared to a planet, and the process actually is pretty different because to form a galaxy, you basically you need this so-called dark matter, which we don't really still understand what it exactly is. But the idea is that this dark matter can basically collect a lot of gas, a lot of material, and which then can form a galaxy. But the process, yeah, is a bit different, but it was a very good question.
So the same like disk, and that's patterning.
Yeah, this is also because of the rotation of the centrifugal force, yeah.
Yes, please.
If I'm allowed, I've actually got two questions. One's not so serious, but the first one is it goes on from what this young gentleman asked about the formation of a cloud. Where the cloud is so dense that the light isn't coming through behind it.
Yeah.
Is that basically what we would know as a black hole then, where a planet is forming, or is that different?
No, it's a bit different. The idea here is that the material of the cloud is just blocking the light, but light can, it's the difference between this and a black hole is that a black hole is an object that is so dense that the light cannot escape from it. So it's a bit different, yeah. Mm-hmm.
Slightly,
Yeah.
not serious
Fun.
question. The difference between when you're forming a rocky planet, you said there's many ingredients. Unlike a Christmas pudding, there's no brandy involved. Is there anything in the creation of a planet?
The brandy comes late. Earth
Yeah,
formed, and
yeah.
now we have brandy. So
Yeah.
the answer is just yes, it takes
Yeah.
about 5 billion years.
Yeah.
Okay, we've got two, let's do two more. We'll do one here and then we'll finish with you, if that's okay?
So if the planet is made of gas,
Yeah.
can you in theory flow through it, or is the gas in the middle so dense and hot that like a core?
It's a very good question. So in principle, in the center, as you said, the gas is so dense and so hot that, of course, it won't be physically possible to fly through it. And sometimes what also happens is that the density is so high that you can form an actual solid core inside this planet. So yeah, it's usually, I would say that it won't be possible to really fly through them.
Okay, and last question.
Yeah, I wondered, do you think in the formation of planets there's sound?
Oof. Well, everything is happening in the space where there is no air, basically, let's say in vacuum. So sound waves cannot really be created, at least not the sound we think about. The idea is that since this disk is composed of gas, you can create sound waves in the gas, so like if the gas was the air. But the idea is that if I am far away from a planet forming, I won't hear anything, but if I am embedded inside the disk, it would be possible to feel sound waves. Yeah.
Wonderful. Okay, so Tea and Biscuits awaits, followed by a planetarium show from the Cambridge Astronomical Association, but can we thank